So from our previous class discussion, if you could remember that we have read that the multiple processes can be stored in memory, and there are two different ways they can be stored. Either is a contiguous allocation or non-contiguous allocation. So initially we were talking about the contiguous allocation, where a process takes contiguous amount of memory, contiguous memory in the while it is being staying in the memory. So for that we have basically three different approaches. One is number of fixed size partitions. Second one is you have a number of partitions but they are of variable size. And the third one we have not discussed, that is the dynamic partition. The dynamic partition says that you store a program. Whenever the first program will come, you store it in the memory and record the limit of it. When the next program will come, you store next to it. So that internal fragmentation will never occur. Internal fragment. So first program will come, it will take 100K suppose. So I'll make a line or I'll keep track of how much byte it has taken, so that the next program will start from 101. Suppose 101 to 300 it will take, the next program will start from 301. So in this case, the fragmentation will not occur. In your variable size partition, we have seen that to keep a process in a particular partition, we may use first fit, best fit, or worst fit technique. Correct? So based on that only, we'll have a problem. We'll solve a problem today. Given 5 memory partitions of 100 KB, 500. So these are the partitions are given. These partitions are given, right? So for example, I say this is the memory. This is the memory. In one part your operating system resides. So maybe upper part or lower part the operating system resides. Now what are the partitions? One partition is of 100 KB. This is of 100 KB. Another is of 500 KB. Let this is of 500 KB. Correct? And some are 200 KB. Sorry. This is 500 KB. Another is 200 KB. Maybe this one 200 KB. Correct? 200 KB. 300 KB. And 600 KB. These are the different partitions over here. 600 KB. These are the partitions over here. So 1, 2, 3, 4, 5. 5 partitions are there. So given 5 memory partitions of 100, 500, 200, 300, and 600 KB in order. So I have written in that order only. How would the first fit, best fit, and worst fit algorithms place these blocks, these processes in the memory? Correct? Similar questions may come into exam as well. Suppose let us see for the first fit. If you go for the first fit, we take the 212. Hello, the 212 KB in first fit means I will go on searching these partitions. The partition is just greater than this, but any of these will be stored over there. So I'll go on searching for the first. It cannot be fit over here. It can be fit over here in 500. So 212K is put in 500K. So what is the fragmentation over here? 500 minus the 500 minus 212 minus 212. This is the fragmentation over here. Understood? Now we'll bring the next one, 417K. When I bring the 417 KB, already this is occupied. This is occupied. So where I can put 417, I cannot put over here. Remaining 212 also I cannot put. I cannot put in 200, in 300. So I'll put it in over here in 600. Correct? So 600, 417 will go to 600. So what is the remaining over here? A partition, what internal fragmentation over here is the 600 minus 417. 600 minus 470. Correct? Similarly, I will bring the next one, 112. If I bring 112, the 112 where it will go? It cannot fit in the first one. Correct? But there is a small partition over here because we have stored, we have taken 212. Some partition is left over here. How much left? Some maybe 8, something like that. It will be stored. 280 kb partition will be left over there. So the partition left in that new partition, this can be, so this 500k minus 200, the first one, the leftover partition has left with 288. Here you have 288 has left. Correct? That 288 was left over here. So in that partition, the 112 can be stored. So in this partition only, the 112 can be stored. So whenever the 426 kV will be requested, there is no space over here where it can be stored. So it has to wait. Is it understood? First fit is understood. I bring one of the process. I go on searching each of the partition where the partition is greater than the process size. If it is greater, I'll put it. Rest space is the fragmentation over there. That partition is left. So whenever the next process will come, I will search again from the beginning. So always I will find a space which is just greater than the process size. So first one, where I will get, I will put it over there. That is the first fit. So what is the fragmentation that will occur in a best fit? Try to understand. Anywhere if you have doubt, you ask me. Now coming to the next one. Now if you go for 212K, this is 212. If you go for 212K, where it can be stored? 212 can be stored in 500, 300 and 600. But which will give you the minimum internal fragmentation? That is the 300K. So 1212K is put in 300K, giving a fragmentation of 300 minus 212. 300 minus 212. Okay, now 417 will come. Now for 417, where it can be stored? 417 can be stored in 500. 417 can be stored in 600. But which will give you minimum internal fragmentation? Is the 500. So second, the 417 is stored in 500. If I go for 112K, where it can be stored? It can be stored in the remaining part of this. It can be stored over here in 200. It can be stored in 300 and the 600K. But what is the minimum internal fragmentation? I will get from 200. So it is being stored in 200K. Are you getting me? We are searching the partition having just greater than the process size, there the process will be stored. So then I bring the 426K process and I found there is only one partition, 600K can accommodate it. We can. Why we cannot store it in 500? Because in 500 already we have stored 417. We have left with space, small space. So therefore we go for 600K. So all processes are satisfied. All processes can be brought to the memory. But in the first case, the last process has to wait. So if you go for worst fit means we will go for maximum internal fragmentation. which partition gives the maximum fragmentation. There I will store. So you bring 212. 212, we found the maximum size is 600K, so it goes to 600K, giving a larger partition. So what is the fragmentation? 600 minus 212. 600 minus 212 is 388. Correct? So 388 is left. 388 is left now, where another process can be kept. So I bring the next one, 417. 417 can go to 500K. So 500 minus 417, that partition will be over here. Correct? Now we'll go for 112. 112 will go for the maximum partition. Maximum partition is now 388K. So it will be stored over there. And 426 cannot be, because the memory is not there. Therefore, it has to, 426 has to wait. Correct? Is it understood, or anyone having doubt? Anyone having doubt on this first fit, best fit, and worst fit? If you have any doubt, you ask over here. Similar problem will come in your exam. Is it clear? Is it understood or not? Anyone having doubt?
Yes, sir.
Okay. So we were talking about the fragmentation. What is this fragmentation? We said that there are two different kinds of fragmentation. This is also important. This fragmentation is also important. Usually a difference comes. What is the difference between internal fragmentation and external fragmentation? Just look over here. Suppose this is my memory, right? There are some partitions over here, right? There are some partitions, maybe fixed size or variable size partitions are there. Suppose this is of 100K. First partition is of 100K. First partition is of 100K. Now, I have a process which is of 98K. Which is of 98K. So I put it over here. Can I put or not? Because the partition is of 100K, I can put 98K. So how much left over here? It is just 2K left over here. Correct? In this 2K, it is very hard to put a program, right? Because to store this data over here, we need more, because those information to keep may take more space. So therefore, this space is being wasted. The memory wastage inside a partition is called internal fragmentation. The allocated memory may be slightly larger than requested memory. I have 100K, I have stored a process of 98K. So maybe 2K is left. That wasted space within a partition is called internal fragmentation. Correct? So one method to reduce the internal fragmentation is to use partitions of different size. We may go for different size, variable size partitions. Is it understood what is internal fragmentation? The fragmentation inside a partition. When the process size is just less than the fragment size, the partition size, then the leftover space is called the internal fragmentation. Correct? So we have 100K, 98K is being reserved, and few space is being left over here. Very few space is left. Correct? This is called internal fragmentation. I think it is clear to everyone. See over here, this is the assigned space. The program is, this is you use space over here, and some space may be left. If it is left, then we say it is a internal fragmentation. Correct? Is it understood to everyone, internal fragmentation? So now coming to the next one is the external fragmentation. Suppose I have 2K left over here. Similarly, I have maybe some 8K left over here. 8K left over here. Maybe in some other partition I have left with 10K over here. Correct? 10K over here. And in some other partition I have an internal fragmentation of another 10K. 10K. And in some partition I have again 5K. Correct? So now first one is 2K, second one 8K, 10K, 10K and 5K. Suppose a new process came with 30K. A new process arrived whose size is 30K. Can I put it in the memory? The first partition has left with 2K, second partition left with 8K, third one with 10K, fourth one with 10K, fifth one with 5K. What is the total memory available? Total memory available is 10 plus 10, 20 plus 10, 30 plus 5. We have available with 35K. But can we put this 30K process over here in this memory? No. Why it is there? Because we have memory available, but they are not contiguous in nature. Because we are allocating the memory continuously, contiguous memory allocations. So these spaces are not contiguous in nature. Therefore, we cannot keep a program in this area memory. This is called the external fragmentation. That means the total free space is the sum of the free spaces is more than the process size, but the operating system is unable to keep that process in the memory. This leads to external fragmentation. Suppose, for example, in a parking area, many cars are being parked. Suppose this is the parking area. In the parking area, the number of cars are being parked. This is one car, this is another car. So, people are parking the car over here. Right? So, you'll find that, there might be some space, more space over here. So, if you'll find this difference, if you sum these differences, there another 1 or 2 car can be kept. Another 1 or 2 car can be kept, but you cannot keep because these spaces, the sum of these spaces is enough where another new car can be kept. Correct? But we cannot keep a new car because these are not contiguous in nature. This is called external fragmentation. This is called external fragmentation. Correct? Internal fragmentation is what? Suppose I have a mark over here that a car can be kept in this area. A small car came over here. If a small car will come, then there will be some space will be waste or not, because a car is a particular space is designated for each of the car. Correct? So if I have 100K memory and we are storing 95, then 5K is being wasted in that partition itself, because in that another process cannot be kept, Correct? That fragmentation is called the internal fragmentation. Is it clear to everyone? Internal and external fragmentation. The total memory space exists to satisfy a request, but it is not contiguous in nature. This wasted space not allocated to any partition is called external fragmentation. The external fragmentation can be reduced by compaction. We'll read it. Is it understood the difference between internal and external fragmentation? Is it understood or not? Having any doubt? Hello? Any doubt on internal and external fragmentation?
No, sir.
Okay, this is another example. Just see over here. There are, this is initially the operating system is stored over here and this space as vacant. So now we try to store these processes. So the first P1 is of 600K. So we take 400 to 1000. Then P2 of 1000K. P2 1000K is being stored from 1000 to 2000. P3 of 300 is 2000 to 300. And I cannot put other process. P4 and P5 cannot be kept because there is not enough space. Now P2 is executing for 5 seconds, so P2 left over. When P2 left over, P2 finishes, this space is now vacant. The memory allocated for P2 is now vacant, right? This 1000 to 2000 vacant now. Now who will come? P3 will come. Sorry, P3 has already there. P4 will come. Now what is the size of P4? 700K. Available is 1000, so we can keep it over here. But how much space left over here? Initially it is 1000 to 2000. We brought only 700. So this 300 is left. This 300 is wasted. It's not wasted, it's free now. Correct? Now I bring the P5. Can I put P5 over here? Can I put P5 over here? P5 is 500. So this is 300 only. This is 260. If you sum these two, this is more than 500, but I cannot keep. Correct? This 300 plus 260 is 560 is greater than 500. I cannot keep because of external fragmentation. So after some time P1 finishes, so this space is vacant, and then the P4 will store over there. P5 will come to that with it. So due to external fragmentation, we are not able to allocate P5. We are not able to allocate P5. Although we have the enough space, we have this 300 and we have also this 260, right? We have this space, but we cannot allocate because of the external fragmentation. They are not contiguous in nature. So next time when I store P5, there is a wastage of again this 100. There is 100. It's a kind of internal fragmentation. I hope it is understood. So now, so one of the solution for this external fragmentation, the solution for external fragmentation is compaction. Is called compaction. Compaction is a very useful technique. What it does, it moves all the used area into one part of the memory and all the unused memory spaces to another part of the memory. Like here, suppose you have three spaces, spaces are free. So what it will do, it will try to move all this free area to one side of the memory, all the used area to the another side of the memory, so that you will have a big hole left. You will be available with a big chunk of free memory area, where a new process possibly can be kept. Correct? So you have process one, memory hole, process memory, like that it is there, and some unused space. So what it will do, it will move all the processes you see over here, all the processes to one side of the memory, and all the memory holes, unused spaces to another side of the memory, so that a new process can be entered over here, the unused space. Okay. So shuffle memory content to place all free memory together in one large block. Shuffle memory content to place all free memory together in one large block. Compaction is possible only if relocation is dynamic and it is done at execution time. So it can only be possible if you could move the processes, means relocation is possible. If relocation is not allowed, then we cannot go for the compaction. Compaction helps to solve the problem of fragmentation, but it requires too much of CPU time because processor will be busy in moving the processes all the time. New processes arrive, I just have to move it. Move all processes towards one end of the memory. This scheme can be expensive because selective shifting is needed. So I just have to select where the processes are not in continuous. So I have to select it, then I have to move it to one side so that you will have a more space available for the new one. But this is one of the technique. This is one of the technique for what? This is one of the technique for reducing external fragmentation. Correct? So what we have read? We have read that there are two types of fragmentation, internal and external fragmentation. To reduce the internal fragmentation, we can go for multiple number of variable size partitions, and to reduce the external fragmentation, we can go for compaction. So till now, whatever the technique we have read, I have not included one slide is the dynamic partition. There are three different partitions. One is fixed size equal number of partitions. All partitions are equal, but their sizes are same. Second one is variable size partitions. I have multiple partitions, but they are of different sizes. So I may go for first feed, west feed, ost feed, or next feed. We suffer two types of fragmentation over here, internal and external fragmentation. To reduce the external fragmentation, we use compaction. Up to this we have read. There is another technique, that is another partition is called the dynamic partition. That is also I said, in dynamic partition what happens, a first process will come, it will be stored, I will put the limit. Second process will come, I will just store exactly next to it. So there will be no internal fragmentation as well. There will be no internal fragmentation in that case. Suppose this is my process, this is my memory. I put the first process, I will keep track of the base and the memory, base and the limit. The next process is stored just next to it. So I'll put the base and limit. I'll put the next process over here with base and limit. So every time a process is being stored, its base and limit are being stored. So there is no internal fragmentation. And but there might be a chance that some memory space may be left at the last. So that external fragmentation may occur, but internal fragmentation will not occur in dynamic partition. That partition is called dynamic partition. So at the run time, it will be decided that how much memory is required, and that memory will be allocated in a continuous fashion. Correct? So these are the techniques that we have discussed for contiguous memory allocation, when the process need to be stored in contiguous memory. But nowadays, operating system do not use contiguous memory allocation. Now, the operating systems that we are using, they use non-contiguous memory allocation. Non-contiguous memory allocation. The process may not be stored in continuous memory area. Correct? If I am opening MS Word may not be stored from 100 to 3000 or 3000 to 5000. This may not be in continuous location. There's some part over here, some part in some other locations. So process is being stored in different area in the memory. Correct? So physical address space of a process can be non-contiguous. Now it is not contiguous, it is non-contiguous. Right? So process is allocated physical memory whenever latter is available. When it is available, it will be stored, but it is non-contiguous in nature. What is the advantages over here? As a part of the process can be stored in different locations, so we may not have external fragmentation. So it avoids the external fragmentation. And it avoids the problem of varying size memory chunks. If you have 3 memory in different locations, you don't need to worry, because wherever 3 memory is there, I will store it a part of the program. If the entire process may not be stored, but a part of the process may be stored. Correct? So try to understand what it does. Very carefully see. Suppose this is my program. This is my program. and this is the memory. Usually this memory is, we expect that memory is greater than this program, but sometimes the program size is also more than this memory size. So now the memory is divided into some fixed size blocks. Try to understand. The memory is divided into some fixed size blocks, and the program, remember, this is program and this is memory. The memory is divided into fixed size blocks called frames, and the page is divided into fixed size blocks. Program is also divided into fixed size blocks. These are called pages. Correct? So first line you understood that memory is divided into fixed number of partitions called frames. Program is divided into fixed size number of blocks called pages. Page size is equal to frame size. That means you take any one frame you take, its size is equal to the size of the page. Its size is equal to the size of the page. So page size equals to frame size. Correct? However, number of pages may not be equal to the number of frames. Page size equals to frame size. However, number of pages may not be equals to number of frames. So as the size of the page and frame are same, so I can take any page and put it in memory, and wherever not required, I will bring it from the memory to this disk. Correct? The size of these frames or pages are in power of 2 to the power 0, 2 to the power 1, 2 to the power 2. In that way it is being there, it is being allocated. Correct? So this information, so a particular page will be stored in somewhere in memory. So it will be stored, which page is stored in which frame is being kept in a table called page map table. Try to understand. These pages are stored in what? These pages are stored in memory. Suppose page number 1 may be stored in frame number 5. Page number 2 may be stored in frame number 1. So which page is stored in which frame, that information is kept in a table called page map table. Correct? The page map table has 2 entries. One is the frame number and another is the offset. Frame number and offset. And these are according to the page number. Page numbers are sequential. Page number 1 which frame, page number 2 which frame. These informations are kept in this PMT. So address generated by the CPU. So processor generates address. Processor generates address which has 2 parts. One is the page number, second one is the offset or displacement. The address generated by the processor, known as logical address, has 2 parts, page number and offset. This page number, just look into this diagram. Just look into this diagram. Here, CPU generates an address. This address is called logical address and it has 2 parts. This is the logical address. Now it has 2 parts. What is that? Page number and displacement. And we know that which page is stored in which frame, and that information is kept in a table called page map table. So this is the page table or page map table where the information is given. The first entry, page 0, in which frame, page 1 is in which frame, page 2 is in which frame. So pages are kept in which frame, those are being stored over those in, just a second. So, so which the pages are mapped into which frames? The pages are mapped, which the page 0 is mapped to which frame, page 1 is in which frame. In that way, it is being stored in page map table. So how many entries will be there in the page map table? Anyone who can say how many entries will be there in the page map table? How many entries will be there in the page map table? I said for each page there is a frame number. Page 0 in which frame, page 1 is in which frame, page 2 frame number. So how many entries will be there in the page map table? Anyone who can answer? The number of entry in the page map table is the number of pages. This is the number of pages. For every page, it must be stored in some memory. So for every page, the frame number is being entered. So if suppose I get the page number 5, so page number 5 may be stored in frame number 10. So I'll get the frame number. So this is one page, page number 5, suppose. In page number 5, suppose there are 10 lines. So I got this frame where it is, this page is stored in memory. The same page, actually this page is stored in memory. Here also there are 10 lines. Suppose I am searching for 7th line over here. I have to go the 7th line over here as well. So I can use the same displacement. I'll use inside the frame to get the physical address. Is it understood? For example, I have two there are two classrooms. One is bigger classroom, another is a smaller classroom. In both the classrooms, some benches are there, some desks are, some benches are there. Right? The bench size are same, whether it is a small room or big room. Right? In one bench, suppose I'll say the 4 people can sit. So if I can move one bench from a big room to small room or small room to big room, but the order in which they are sitting, that is not being changed. Those are not being changed. So third person who is sitting over here is also third person in that smaller room. So if there might be number of addresses inside this page. So if it is 5th line, I'll just go for 5th line over here. Therefore, the displacement is same. And I'll get the physical address. Correct? The starting address of this table is stored in a register. It's called page table base register. Page table base register, which keeps track of the starting address of this table. So whenever a page is created, it's actually added with this PTBR so that it will get the corresponding frame number. From the frame number, we'll add the displacement to get the physical address. This is very, very important. Question usually comes to draw the diagram and explain how the logical address can be converted to physical address. So look over here. This is the logical memory. Logical memory, we have page 0, page 1, page 2, page 3. This is my program, has 4 pages. Page 0 is stored in frame number 1. Page 0 is in frame number 1. Correct? Page 1 is stored in frame number 4. Page 2 is stored in frame number 3. Page 3 is stored in page number 7. So I keep in a table, the page map table. The starting address is stored. So whenever I search for, suppose I have every page has, suppose 5 blocks are over here, 5 memory locations. Such I am searching for the 4th one. So I will go to this page number 2 and I found that it is in frame number 3. So I will go to frame number 3. I found page number 2. So this page is over here. So therefore, this must have also the same length over here. I have 5 pages. I need the 4th one, 1, 2, 3, 4. So I'll go to 1, 2, 3, 4. I'll get this one. So this is called the displacement. So I use the displacement to get the information. So correct, this table is called the page map table, and the starting address of this table is stored in a register called page table base register. This is another example. Just inside the, so this is page 0. Inside the page 0, I have stored some value. Page 0 is stored in frame number 5. This is page 0. This is stored in frame number 5. 0, 1, 2, 3, 4, 5. So this 0 page is stored over here. The page 0 is stored over here. Correct? Now, the order you see, I have A, B, C, D, the order in which I have stored. This is the same order I have stored. So if I have to get the third one, here also I have to get the third one. So displacement is same. I just need to keep that which page is stored in which frame, and that information I have kept over here. The page 1 is stored in 6. The page 1 is stored in 6. So that information we have kept over here. The 2 is stored in 4. 2 is stored in 1. So this is being, this information is, this is in 1. So this information is kept over here. Correct? And this is on 2. And that information is also we are keeping over there. Correct? Once we get that in which frame it is being stored, then we can move inside that frame and get the corresponding value. Is it understood? Is it understood? Or anyone having doubt?
No, sir.
Okay. So what we have, we may have some internal fragmentation, like suppose page size is 2048, process size, page size is which one? These are the page sizes. These are the page size that the operating system has decided what is the page size. Page sizes are fixed. Do remember, page size are fixed, frame sizes are fixed, page size equals to frame size. Page size equals to frame size. And now we'll say what should be the size of the page? It should not be too small. If it will become too small, what will happen? You will have more number of pages and there will be more entry in the page table. So page table will take more space. So now you will say that I will have less number of pages. I will have bigger size pages. If you will have bigger size pages, I might be requiring a part of it, but you have to load the entire page over into the memory. So that is a trade-off between this size of these pages and memory size. So what you will do, it should not be too small or too big. So if the page size is 2048 and process size is somewhat like 2072,766. Okay. So if you divide this with the page size, you will see that there are 35 pages plus these bytes. If you divide it, you will get it, right? Because page is 2048, process size is somewhat like this, correct? Process size is more than this, the process is divided into some pages. This is my program, correct? What is the size of this? The size of this is 7248, correct? I have to divide into some pages. I have to divide into some pages. This page size is 2048. So how many number of pages will be required? 35 number of pages plus for the another page I require only this. So what is my page size? Page size is 2048. So some spaces may be 2048 minus 1086. Some spaces may be wasted, but it is manageable or acceptable because many of the spaces we are actually utilizing. Correct? Few internal fragmentation may occur. So worst case internal fragmentation, a process need n frames plus 1 byte resulting n plus 1 frames. Suppose I'll say here only 2 bytes. After 35 pages, 1 byte left. So for 1 byte, I have to take another page. Then it's a wastage of the entire partition over there, the entire page over there. Correct. So average internal fragmentation 1/2 page per process. Sometimes on an average it occurs. So smaller page size is desirable. It is there, but smaller page size also have some disadvantages. Like if you have smaller page size, more number of entries has to be more number of entry has the page table will have more number of entries. Correct. Typical page size is kept between 4K to 8 KB. This is being managed by the operating system, right? Some CPU and kernel support multiple page size. So I suppose 2 page, sometimes it have 2 different page sizes for different processes. So this is about the pages. To keep track of the free frames, I have to put the pages into these frames. So I must know that which are the frames that are free, correct? So this free frame list has to be kept somewhere. Free frame list, those free frames are in which of the frames are free, so that new pages can be allocated. When a new page arrives in the system to be executed, we have to express its size. If the size of process is n page, then we should have at least n free frames, right? So every time I cannot go for searching, I just have to put a table that which pages are free. So I have a free frame list. I'll have a free frame list. That means these frames are free where these frames are free where the pages can be kept. This is called the free frames. Correct? So when a page is loaded into a frame, the frame number is put into the page table. In paging, the user views memory as one single space containing only this one program, but actually the user program is scattered throughout the physical memory. So although we are suppose working with MS Word, we are assuming that Word is stored in contiguous memory, but it is not actually like that. It is being stored in different memory locations. Different pages are stored in different memory locations. Our MS Word is divided into pages. Each of the page may be stored in different memory locations. That information are kept in page map table, and the free frames of the memory are being stored in separate list, that is called the free frame list. So this is all for the today's class. Any doubt if you have, you ask me. Between I will take the attendance. Roll number 1, roll number 2 is absent. 3, 4, 5, 6, 7 is absent. Roll number 7.
So 7 present.
Present, okay. 13. 21, 22, 25, 27, 30, 34, 37, 39, 41, 43, 50, 55, 58, 67, 73, 'Roll number, I repeat the roll numbers who are absent. Roll number 2, 13, 22, 25, 27, 30, 37, 39, 43, 50, 55, 58, 67 and 73.